Last class we started talking about rigid body motion, and we're going to continue the story of rigid body motion. If you remember, rigid bodies are just everyday objects with distributions of mass or matter. So in the last class, we discussed the particular case of rigid body equilibrium. And in today's class, we're going to move on to rigid body motion. And so in the last class, we talked about torques. In this class, we're going to talk some more about torques. In the last class, we talked about center of mass of a rigid body. We're going to talk about another quantity, the moment of inertia of a rigid body in today's class. And we're going to work our way through rigid body motion. Specifically, on this slide here, these are the topics I want to go through. I want to introduce what we call Newton's law of rotation, and it's a sort of a parallel of Newton's law of rotation. So we're going to talk about Newton's second law of rotation, and we're going to see it's a parallel of Newton's second law of motion. I'm going to talk about the moment of inertia of a rigid body. It's a quantity that reflects the mass and mass distribution of a rigid body. It's sort of another quantity like center of mass of a rigid body, reflected the mass and the matter distribution of a rigid body. So that's the second topic. And then finally, we'll talk about what's a very famous, a sort of classic problem in rigid body motion. And it involves the motion of a solid sphere, a solid cylinder, and a ring. They're all rigid bodies because they have mass, they're distributions of mass and matter. And we're going to examine the problem of the sphere, the cylinder, the ring rolling down an incline. And so this is really a very famous, the most famous example of rigid body motion. So that'll be our third topic. Okay, so as a reminder, when we talked about rigid body equilibrium in the Tuesday's class, the meaning of rigid body equilibrium was that a rigid body is in equilibrium if the sum of the forces acting on it add up to zero, so there's no net force, and the sum of the torques acting on it add up to zero, and so there's no net torque. And so these two conditions are rigid body equilibrium. And if there are no forces acting on the rigid body, then there's no acceleration of the rigid body. And for example, if it's at rest, it will stay at rest. If there's no torque, no net torque acting on the rigid body, there's no angular acceleration. And if it's at rest, it will again stay at rest. So that's rigid body equilibrium. And what we're going to talk about today is really the case of when there are forces acting, net forces acting on a rigid body, when there is a net torque acting on a rigid body. And that's rigid body non-equilibrium. And in that case, what happens? Well, if there's a net force on the object, you get a non-zero acceleration of the object. It's going to speed up or slow down or change its direction. And if you've got a non-zero net torque on an object, that rigid body is going to rotate faster, rotate slower, change from clockwise to counterclockwise rotation or vice versa. And so that's the world that we're exploring. We're going to explore this world of how torques and forces on a rigid body will create acceleration and angular acceleration, changes in motion of the rigid body. Okay, so this is just a quick reminder. Of course, we all know this. It's Newton's law of motion, Newton's second law of motion. And I'm just reminding us of Newton's second law of motion because we're going to talk about Newton's second law of rotation. So if you remember, Newton's second law of motion says that the acceleration of an object, of a rigid body, for example, the acceleration is dependent on the force, net force on the object, and it's dependent on the mass, the amount of matter, what we call the inertia of the object. And specifically, the acceleration that arises due to the force is in proportion to the force and in inverse proportion to the mass or the inertia. So, you know, a bigger force on a rigid body will create a greater acceleration of the rigid body. A smaller force, a lesser acceleration. If you exert the same force on a heavy object like an elephant, there's not much acceleration. Same force on a light object like a mouse, there's lots of acceleration. So all that is embedded in to Newton's second law. It's really how we understand the influence of forces on motion, how forces exactly change motion. Well, here's Newton's second law of rotation. And it's really an analogous law of rotation to that one for motion, translational motion. It talks about, rather than the acceleration of the rigid body, the angular acceleration of the rigid body about some axis. It talks, rather than about the force, the net force on the rigid body, it talks about the net torque that's acting on the rigid body. And the law, like the second law of motion, contained mass or inertia. This law contains another sort of analogous quantity. It's rotational inertia, or what we call moment of inertia. And so let me just introduce the law here. It's just this simple equation. And it says that the angular acceleration of a rigid body is equal to the torque that's exerted on the rigid body divided by this, this moment of inertia, or rotational inertia of the rigid body. And each of those three items in that little equation play the same role as the corresponding items in Newton's second law of motion. So, you know, the torque, tau in the equation, that's that twist or turn that changes the motion of the rigid body. Like the force was the push or the pull that changed the motion of the rigid body. The moment of inertia or rotational inertia, I'll call it both these things. It's given a symbol I here, and that's kind of the object's resistance or reluctance to having its rotational motion changed. Like mass or inertia, m, was the kind of resistance or reluctance of a body to having its translational motion changed. And then finally, we've got angular acceleration over on the left-hand side. So that angular acceleration, that's analogous to linear acceleration in Newton's second law of motion. In both cases, they're the response to the force or the torque. So the response to the force or the torque is a change in motion, speeding up, slowing down, changing direction. In one case, it's measured by linear acceleration, in the other case, angular acceleration. So I would say just think of this as a copycat of Newton's law of motion, but for rotational motion. All the quantities in this law are the same as the quantities in Newton's second law for motion, but for the rotational equivalent. So instead of force, it's torque. Instead of acceleration, it's angular acceleration. Instead of mass or inertia, it's rotational inertia. And actually, I'm not going to show this, but it's not really hard to show that this Newton law of rotational motion actually is a consequence of Newton's second law of translational motion. You can show that. It's not some new law, really. It's just a different version of the old law, a version applied to rotations rather than to translations. Okay, I'm just going to make a couple of remarks about it on this slide, just quickly. One about the units of the quantities, and one about the nature of the quantities. So units over here on the left-hand side. Torque, like force, is a vector. It does have a direction as well as a size. Angular acceleration, like linear acceleration, that's a vector. Does have a direction as well as a size. That's why they're underlined in this equation, to indicate they're vectors. Moment of inertia, on the other hand, like mass or inertia, that's a scalar quantity. It just has a size. So in our work on rotation, like in our work on translational motion, an object's mass is important in determining how it responds to forces, and that's just a number. And an object's moment of inertia, rotational inertia, is just going to be a number in understanding how an object responds to forces. So did I just describe that they were the vector nature of these things, which was actually over here? But anyway, I also want to describe the units, which is over here on the left. So the units of these quantities are different. Torque has units of newtons meters. We've already met that from the definition of torque in terms of force. So torque has units newtons meters, force had units of newtons. So they're different. The units of the angular acceleration, that's radians per second squared. That's different from the units of linear acceleration, meters per second squared. And so those are different. The accelerations have different units. And then finally, the rotational inertia, moment of inertia, and mass, they have different units too. So it's kilograms meters squared for rotational inertia or moment of inertia. It's just kilograms for mass or inertia. So the units of these quantities are different, although they play corresponding roles, equivalent roles in rotation translation. And then here's this comment that I kind of already introduced. The angular acceleration is a vector. The torque is a vector, as we know. This new quantity, the moment of inertia or rotational inertia, that's a scalar. Okay, so let's look at an example. Let's just get straight on, right? Let's not mess around. Let's look at an example. And in this example, we've got a potter's wheel. We're told its radius, 0.52 meters. We're told its rotational inertia, 10 kilogram meters squared. And we're told it's rotating initially at 49 revolutions per minute, 49 turns per minute. We're told then that the potter, I'm the potter, right? I'm gonna stop the wheel, and I'm gonna stop that wheel rotating in 4.5 seconds. And the way I'm gonna stop it is that I'm gonna apply a wet rag to the rim, push a rag on the rim, and that will slow it down by frictional force between the wet rag and the rim. And we're actually going to go on and calculate the coefficient of friction in this situation. And so that's the plan here. I even made a little video of this, since I am an avid potter. let me show that. I've got to share a different screen. Okay, I hope you can see. This is my potter's wheel at home, and I mounted an arrow on it for some reason. And I'm going to start it spinning. And then I'm going to do exactly what the potter in the question does. I actually didn't have a wet rag, but I had a wet hand. And I'm just going to, I'm pushing my hand towards the axis of rotation, but that's causing a frictional force between my hand and the wheel, and it slows the wheel down. And it took 4.5 seconds to do that. So that's the situation that is discussed in this particular problem. Let me go back to my slides. And let's calculate the coefficient of friction between the wet rag and the potter's wheel. Let's see if we can do that. I got to get my pen going again here, I think. Okay, so when I solved this problem, there were really two parts of it. There's a first part that was about rotational kinematics. So that's sort of a reminder of things we've done in the past. And then there was a second part involving this rotational dynamics of the rigid body. That's the new thing we're doing now. The kinematics part was, so I needed the angular acceleration of the potter's wheel. Because that angular acceleration is related to the torques, and that those torques are related to the forces, and that's how I'm going to get at the frictional force and the coefficient of friction. So first, I actually had to do kinematics to get the angular acceleration. Then in the next slide, we'll go on and find out the coefficient of friction by analyzing the forces and torques. So I, of course, made a sketch. It's over here on the left-hand side. Here's the potter's wheel in blue, and that's the axis of rotation. It's rotating. In my picture, it's rotating clockwise. I know the initial angular velocity, omega naught, 5.1 radians per second. I called it negative because it's the convention for clockwise. I know the final angular velocity, it's 0, it comes to rest. I know the elapsed time that it took me 4.5 seconds. We all saw that. That's the information I know. And I want the angular acceleration because it's that's related to torques and will get me through their relation to forces, to the forces, which will get me to the frictional force and the frictional coefficient. So that's the plan here. Okay, so I thought back to the equations of rotational motion that were also parallels. They're parallels of the equations of linear motion. And I thought about this particular equation. It relates the initial and final angular velocities, the angular acceleration, and the elapsed time. That's exactly what I need to calculate alpha, the angular acceleration here, from omega, omega naught, and t. All these things I know. And so all I had to do, this is simple, I'm going to go really quickly here. I just plugged in the initial final angular velocities, plugged in the elapsed time, and calculated this angular acceleration. And it was about just over 1 radian per second squared. You notice it's positive, whereas the rotation was negative. The rotation was clockwise. The angular acceleration to slow the potter's wheel down must be counterclockwise. So they're in opposite directions. That makes sense. Okay. Now the more fun bit, I think, the more interesting bit. Now we're going to move on from kinematics to dynamics, and now we're going to involve our laws of rotation, second law of rotation. And ultimately, we're going to calculate the coefficient of friction. So I redrew things over here on the left-hand side, and I added to the drawing some information, some additional information that we didn't need when we were thinking about just the kinematics. So we know the radius of the potter's wheel, and we know the moment of inertia of the potter's wheel. So those two numbers we were told, and they're important for this second part of the problem. We were told that I, the potter, pushed towards the axis of rotation with a force of 68 newtons. So that's my push on the potter's wheel. It's towards the axis of rotation. I've written it N equals 68 newtons because it's really a normal force. I'm pushing perpendicular to the surface, right angles, normal to the surface. So that's a normal force I'm creating in magenta there. And as you know, right, when you have a normal force between two objects, then there's an accompanying frictional force in general between those two objects. And there's a frictional force in this case between the two objects. And that frictional force and that normal force are related to one another. Here I pictured the frictional force in green. It's parallel to the surface, it's tangent to the circle, and it's related to the normal force through the coefficient of friction. And so that's a very important picture that helps me solve this problem, I think, because I'm really visualizing, imagining the forces that are acting, normal force and friction force. Now, the second important point, after imagining the two forces that are acting when I push the wet rag on the potter's wheel, is to understand that those forces in general make torques. Now, in this case, what is interesting is that the normal force which acts towards the axis of rotation, if you think of that formula, that general formula for the torque, let me just write it down. Tau equals F R sine theta. Think about that formula, and think about that formula for the normal force and the friction force. For the normal force, well, there is a normal force, 68 newtons. It is applied some distance from the axis of rotation, 0.52 meters. But the normal force and the vector from the axis of rotation to where the force is applied, they're 180 degrees to one another. One of them is towards the left on my sketch. One of them is towards the right on my sketch. There's 180 degrees between them. Sine of 180 degrees is 0. And so although there is a normal force, it's not creating, it's not making any torques on the potter's wheel. It's only the frictional force in green here, the torque. And so we're going to apply the law of rotational motion. I've written it here. I've written it rather than acceleration equals torque divided moment of inertia. I've written it as torque equals acceleration times moment of inertia. And in the middle here, I filled in my understanding that in this case, right, that torque is created by a frictional force. The size of that torque is the friction force times the distance it's applied from the axis of rotation times the sine of the angle between the direction of the force and this vector to where the force acts. That's 90 degrees. I fill all that understanding in. And then finally, I fill in the fact that I know that that frictional force has a magnitude that's related to the normal force. It's the coefficient of friction times the normal force. And I get this fantastic equation here. That equation, if you look at the right-hand side of it, is telling you the relationship really between the known normal force and the resulting angular acceleration. And we know those things. So I can actually take this equation over here and rearrange it for the unknown coefficient of friction in terms of the normal force that we applied, the angular acceleration that we observed, and these quantities R and I that describe the potter's wheel, the radius of the wheel and the moment of inertia of the wheel. And then it's just, I mean, this is now straightforward. I just plug in the numbers. This is in the numerator here, this first term is the moment of inertia, 10 kilogram meters squared. Second term is the angular acceleration we calculated, 1.1 radians per second squared. In the denominator, we got the normal force, 68 newtons, and the radius of the potter's wheel, 0.52 meters. We plug in them all in, and here's the result. 0.31 was the coefficient of friction between the potter's wheel and the wet rag. If that coefficient had been larger, then there would be a bigger frictional force, there would be a bigger torque associated with the frictional force, and the angular acceleration would have been larger, so the wheel would have stopped faster. If that coefficient of friction had been smaller, then there would be a smaller frictional force, there would be a smaller torque associated with the frictional force. And again, there would be, in this case, less angular acceleration, and the wheel would have taken longer to stop. So that's a nice example of rotational dynamics, of second law of rotational motion. In that example, we were actually just told what the moment of inertia was. So somebody had to have gone and figured out what the moment of inertia of the potter's wheel was. What I'm going to do now is show how you might calculate and illustrate calculation of the moment of inertia. And again, let me just stress that when we talk about rigid bodies, like blocks, like buckets, like crates or whatever, some everyday thing with size, shape, and distribution of matter, there are these two quantities that we use in the description of the rigid bodies. They're important for analyzing motion of rigid bodies. One of them we've already handled, that's center of mass. We needed that when we did the rotational equilibrium. The new one we need is moment of inertia. You need that when you're doing rotational motion. So we're going to go on and see how to calculate that. It's not hard. First, I want to give you a concept of rotational inertia, a moment of inertia. This thing we give the symbol I. Just like center of mass, which depends on the mass and where it's located, moment of inertia is dependent on the amount of mass and where it's located. And as an example, I constructed this, it took me way too long, but I made this little figure. So the stick figure is me, and I wanted to carry out a demonstration. I wanted to come into class, come in a large lecture room, and show you, I was going to swing around my head a mouse and an elephant. And I was going to swing around my head the mouse and the elephant on a short string and a long string. So let me point this out here. This is the short string, the little r, and the small mass mouse. Over here in the bottom right, this is the long string, uppercase R, and the heavy elephant, uppercase M. And then there are other combinations, right? I put the mouse on the short string, and I put the heavy elephant on the, no, put the mouse on the long string, and I put the heavy elephant on the short string. So those are I've got two masses and two strings. Those are the four combinations. Okay, so rotational inertia, moment of inertia, depends both on the mass and on the location of the mass. The situation, the object on the string with the smallest moment of inertia, that's easiest to swing around my head, is this case here. It's when I got the smallest mass and it's nearest the axis of rotation. So here, M and R are small. That's very easy for me to swing the mouse on the short string around my head. The most difficult one to swing around my head is this one here. Now I've got the elephant, the object with a large mass, on the long string. So it's a long way from the axis of rotation. That makes it very hard to swing the elephant on the long string around my head. So this is very hard. This corresponds to a very large moment of inertia. This is very easy, corresponds to a very small moment of inertia. So moment of inertia, or rotational inertia, is a measure of how easy or difficult it is to change the rotational motion of an object. It's easy to change the rotational motion of the mouse on the short string. It's much harder to change the rotational motion of the elephant on the long string. The other cases are somewhere in between. So this case here, mouse on long string, in this case here, elephant on short string, are somewhere between the easiest and the hardest, in the top left and the bottom right. I want to show you a demonstration of moment of inertia. So I'm going to share another slide here, another screen. Okay. So here I am in the large lecture room, and I've got a meter stick, and I've actually got two blocks. And I'm going to demonstrate how easy or hard it is to swing the meter stick with the blocks affixed to the meter stick, where the blocks are fixed at different locations. So this case here, let me stop it for a moment. This has the masses at the end of the far end of the meter stick, like the mouse on a long string, or the elephant on a long string. So this is going to be a large moment of inertia. And I'm going to try and swing this, change its rotational motion as fast as I possibly can. And that's the best I could do. It's absolutely the best I do. I had to go to a physical therapist after doing this. I hurt my elbow. Now I'm going to put the masses close to the axis of rotation. This is like the mouse and the elephant on the short string. And I'm going to again see how rapidly I can swing this object to and fro, which now has a much smaller moment of inertia. And look, I remember this, so easy. It was just so easy to rotate it, change its rotational motion. So that's a small moment of inertia. And so that's a demonstration of moment of inertia, and how it depends on mass, but it also depends on the location of the mass. So let's go back to my slides. And I've got to get the pen going again. And well, we always want equations, don't we? We always want formulas. We always want recipes, accurate recipes for calculating things. And we want a recipe, a rule for calculating the moment of inertia. And so I put a couple of equations on this slide. Let's start on the left-hand side over here. So this is how you calculate the moment of inertia of a point mass, or a small mass, on a string. And so that's what's depicted in this picture. It's a little hard to see, but here's the small mass, little m. Here's the string, length r. This is the axis of rotation in the center of the table here. And the moment of inertia of that mass on that string about that axis, that moment of inertia I, depends on the mass, depends on the location of the mass in this way. It's mr squared. There you see, right, why it has the units of kilogram meter squared, because mass has the units of kilograms, and the this distance from the axis of rotation has the units of meters. So that's a simple rule for calculating the mass of the moment of inertia of a point mass about some axis. That's actually a building block for calculating other moments of inertia. So the moment of inertia of an assembly of masses, a collection of masses, is just given by this equation here, where really you just add up the contributions of each mass. So take a look at this picture here. I'm imagining a disk, and I'm going to imagine that I break up in that disk into lots of little pieces. So there's one piece down here. I'm going to call its mass m1 and its position r1 from the axis of rotation. There's a second piece here. I'm calling that's mass m2 and it's a distance r2 from the axis of rotation. And then there's a third piece, and that I've called mass 3. It should be somehow got the, yeah, sorry, this one was mass 2, and it's a distance r2 from the axis of rotation. And I could keep, you know, I got bored, but you could keep going and going and going and breaking up the whole arrangement, the whole distribution of mass into lots of little pieces of mass, like lots of little point masses that look like the point mass over on the left-hand side of this slide. To get the total moment of inertia, you just take the moment of inertia of the first little mass, the moment of inertia of the second little mass, moment of inertia of the third little mass, and so on and so forth, and you just add them up, total them up. And so that's a recipe for calculating the moment of inertia of a collection or a distribution of mass. And here I'm just writing it symbolically. This is a sum, a summation over I. I would go like 1, 2, 3, 4, 5, and I'm just counting up the mr squares of the first little mass, the second little mass, the third, the fourth, the fifth, and so on. And so those are two handy formulas for calculating moments of inertia. They tell us, right, firstly, that what we just experienced with the mouse and the elephant, or with the demonstration, that not only does mass count in the moment of inertia, but where it is counts. If it's a long way from the axis of rotation, that makes the moment of inertia large in these equations. If it's close to the axis of rotation, it makes the moment of inertia small in these cases. Okay, so in physics, there are some common shapes, some common geometries where somebody has already calculated the moment of inertia for us, for those common geometries. And we often just use the equations that describe the moments of inertia of those geometries. And so I've just listed them on this table here, so that you just think of this as like a reference document. If you're working with a problem with a cylinder or a sphere or a ring, you can consult this document to look up what the moments of inertia are. And this is, you know, of course I stole it from the textbook, actually. I'll just mention a couple of them. So over here on the top left, so this guy here, this is a ring of radius r, and all the mass is located at a distance r. And if you look at its equation for moment of inertia, it's just mr squared. It looks just like the equation for a single point mass, because in this case, all the mass is still at a distance r from the moment of inertia. distance r from the axis of rotation. If we were to think of a cylinder, on the other hand, a solid cylinder, now I've filled in the whole cylinder with matter. So some mass is at a distance r, but some mass is much closer to the axis of rotation. Some matter is zero distance from the axis of rotation. Here, in this case, the moment of inertia is smaller. Look, there's this factor of a half here. And that's because, well, not all the mass is a distance r from the axis of rotation. Some is closer. And the details of how much closer, how much mass is, gives this factor of a half. One other case I'll look at. This is a sphere up here on the top right. In the sphere is the solid sphere, is the geometry where you pack the mass so you can get it as close as possible to the center of the sphere. So that's kind of a special geometry where you're trying to put the mass as close as possible. And that geometry has the smallest moment of inertia of these objects here. And it has the smallest moment of inertia. You can see this is 2/5 compared to 1/2 over here, and compared to 1, effectively 1 here. Okay, so I've given you a formula for calculating moment of inertia, and I've also shown you that there's familiar geometries where you can just look up the moment of inertia. I want to work through one quick example of a moment of inertia. Okay. So as an example, let's calculate the moment of inertia of a mass distribution. And I'm going to take this particular mass distribution. So this is a mass distribution that really just involves 3 point-like masses. So there's one here. Oh. This always happens to me. There's one here. I think I'll be calling that mass number 1. And it's 2 centimeters from this axis of rotation. There's a second mass here, 2 kilograms. It's 4 centimeters total from the axis of rotation. And then there's a third mass here. I'm sure I'll be calling that M3. It's 6 centimeters in total from the axis of rotation. And so we're going to imagine swinging this. Imagine it's a massless string that connects all these. And now we're going to swing that around our head. And we want to know the moment of inertia of this particular arrangement of masses on the string. And so we're going to calculate that rotational inertia. And so this is my calculation of this object's moment of inertia. And what's important here is this idea that the moment of inertia that I talked about, the moment of inertia of this arrangement of masses is just the sum of the moment of inertia, the individual contributing masses. And so I'm going to write that moment of inertia I as the sum of a moment of inertia I1, moment of inertia I2, moment of inertia I3 of the 3 individual masses. That's the basic idea here. That's my approach. And that's what I'm starting with here. This is the moment of inertia of the entire object. And the I1 and I2 and I3 are the moments of inertia of the 3 individual masses. And indeed, when I labeled this diagram, I called this mass 1, M1, and this is its distance, R1, from the axis of rotation. This is mass 2, M2. This is its distance 4 centimeters from the axis of rotation. And this is mass M3 and its distance R3 from the axis of rotation. So that's how I'm denoting, labeling the masses and the distances. Okay, so then I just need to, for my expression for the moment of inertia, fill in the equation for the first mass, fill in the equation for the second mass, fill in the equation for the third masses. I've got the 3 masses M1, M2, M3. I've got the 3 distances, R1, R2, R3. I know every one of these numbers, right? That was pretty easy. I just start plugging them in, slinging them into the equation, and then multiplying them, each mass, by the square of its distance from the axis of rotation. You'll notice an interesting feature when I do that. The masses were getting progressively heavier, further and further from axis of rotation. The distances were getting progressively further and further from the axis of rotation. Now the masses were 1, 2, 3. So the second mass was twice the first mass. The third mass was 3 times the first mass. Likewise for the distances, right? The second distance was twice the first distance. The third distance was 3 times the first distance. Now the moment of inertia goes as the product of the mass and the square of the distance. So the second mass, which has twice the mass and twice the distance, will have 2 times 2 squared, 8 times the moment of inertia of the first mass. And you see that there. And then the third mass is 3 times the mass, and it's at 3 times the distance. So it'll have 3 times 3 squared, whatever that is. That's 27. 27 times the moment of inertia of the first mass, and that's what you see here. And so I added them all up. This is the total moment of inertia of the arrangement. But it's interesting to see that that mass 1, which is so close to the axis of rotation, hardly contributes anything to the moment of inertia. Overwhelmingly, it's mass 3, which is furthest from the axis of rotation, that dominates the moment of inertia. Okay, let's move on. I got a second example in my lecture slides here. I'm not going to solve this right now. I will solve it sometime after class and post it as an example in modules. I've sometimes been doing that. I don't know that I've really told you that I'm doing that, but maybe you've seen the examples that I post in modules. So I'm going to skip this one because I really want to get onto. I mean, this is something I really enjoy, this problem, this classic problem, famous physics problem of a rolling sphere, cylinder, and ring. So I want to get onto this. And so here's the problem that we're going to analyze. We're going to imagine for the sphere, the cylinder, and the ring, I've taken a blueberry, a donut, and a cookie. And I put them on the top of a ramp, put them on the top of an incline, and I'm going to release them simultaneously. And I'm going to let them roll down the ramp. And the question is, who wins this race? This is a fantastic race. And who's going to win the race? Is it going to be the blueberry? Is it going to be the donut? Is it going to be the cookie? Or maybe it's going to be a dead heat. Maybe the whole thing will be a dead heat. In fact, it's tempting to think it will be a dead heat. Think back to those early days of this semester. We talked about Galileo's law of falling bodies. And we learned that once we strip away the air, once we strip away the air resistance, all objects fall under gravity with the same acceleration of gravity. The mouse and the elephant fall, the feather and the hammer fell with the same acceleration of gravity. And so it's kind of tempting to think, well, look, this is just another example of that understanding that we met in those first few lecture classes, that all objects fall with the same acceleration of gravity. the blueberry, the cookie and the donut, or the sphere, the cylinder, and the ring will fall with the same acceleration of gravity. But the point is, we are not dealing with simply falling blueberries, cookies, and donuts. The cookie, the donut, and the blueberry are rolling down the incline. And that's the difference. And that's going to make the results different. And so Baxter's here to tell us or remind us that this is a more interesting, complicated problem. We've got falling, right? The objects are moving downwards towards the floor, down the incline, but they're actually rolling down the incline. And so there's both translational motion going on in this problem, and there's rotational motion going on in this problem. And specifically, the way we tend to think about it is the following. So this in green, oh, just can't stop myself with that. In green is either the, the sphere, the cylinder, or the ring. Could be any one of them. But as it rolls down the incline, there's both rotation and translation. The way we tend to think about it is, think of this point here. That's the center of mass. Its motion is just straight down the incline. And so that center of mass undergoes translational motion. And then any other point, there may be a point on the surface here. If you think about its motion with respect to the center of mass, it's just undergoing rotational motion around the center of mass. And so that's how we break out the translational motion and the rotational motion. We break it out by using this concept, idea of the center of mass. Every object has a center of mass. And for this sphere or cylinder or ring, the center of mass is just undergoing translational motion down the incline. And all the other bits and pieces of the solid cylinder, sphere, or ring are rotating, undergoing rotational motion about that center of mass. Now, that's what rolling is. That's what we mean by rolling. In rolling, there's both rotational motion and translational motion. And in rolling, if it's rolling without slipping or sliding, there's actually a simple relationship between the kinematic quantities of the translational motion of the center of mass and the rotational quantities of the rotational motion of the rigid body itself. And that's what I've written down here. So this is an important thing that we're going to use in solving this problem. Over here, X, V, and A, those are the quantities that describe translational motion. And in this case, the translational motion of the center of mass. Over here on the right, theta, omega, and alpha, they're the quantities that describe rotational motion. In this case, the rotational motion of the rigid body. And if this blueberry and donut and cookie are rolling down the incline, those rotational, translational, kinematic quantities are related in this way here. They're related through the radius of the rotating blueberry, donut, or cookie. That's what the R is here. And so that connects together. So when these objects roll down, there is rotational motion, there is translational motion, but they're not independent motions. They're related motions because the rolling sphere, cylinder, and ring are not sliding. They're just rolling. That's really what we mean by rolling. This is kind of the physics definition of rolling. So if you went up to a physicist in the street, right, and you said, what does rolling mean? You get an answer like these equations here. I mean, maybe you would. Okay, So now, well, look, right now we've become experts in equations of motion and equations of rotation. And we got here both motion and rotation. So let's apply our equations. And so that's what I'm going to do. On this slide, I'm just going to generate two equations describing the dynamics of the, I'm looking at the clock because I want to make sure I get this problem completed. It's so fantastic. So I think I'm okay. I want to write down on this slide the equations that describe, encapsulate the rotational and the translational motion. So to start that, I made this sketch here of the rolling sphere, cylinder, or ring in green, and the various forces that are acting on it. And it's quite a sophisticated sketch, I think. I was quite proud of it. So I've got the incline here. It's at angle theta. I've got the sphere or whatever here in green. And then I've marked on three forces. Here's the weight. But I've been careful here. I've put it acting at the center of mass because now we're dealing with rigid bodies and that's where it acts. I've got the normal force and I'm being careful here. I'm putting where it acts. It's at the contact between the rolling body and the surface of the incline. And so that's the normal force. Labeled it N. And then finally, there's a friction force. If there wasn't friction, you wouldn't get the rolling. You just get sliding. And that also, I've been careful. I've put it where it acts. It acts at that point of contact between the rolling object and the incline. So those are the three forces, the weight W, the normal force N, and the frictional force F, subscript F. And those are the ingredients in writing down the equation that describes the translational motion and writing down the equations that describe the rotational motion. So let's go ahead and do that. Let's start with translational motion. That's this guy here. I'm going to call this equation number 1. And the key thing here is that we can, as we have done in the past, resolve the weight into two pieces. One that's perpendicular to the incline and one that's parallel to the incline. The one that's perpendicular, W cosine theta, just balances the normal force. They just counteract each other. All the interesting stuff that creates the acceleration is in the direction parallel to the incline. And so I'm going to apply Newton's second law of motion to this direction parallel to the surface of the incline. And in that direction, I've got a component of gravity, mg sine theta, that's down the incline. It would be this piece here. And I've got a frictional force that's up the incline. It's this force here. And mg sine theta and F, subscript F, those are my notations for the sizes of those forces. And they're in opposite directions. So I called downwards positive, and I called upwards the negative direction. Those are the two forces that add along the incline, and they govern the acceleration through the second law of motion. And so that's our first equation. And then our second equation is over here downstairs. I've called it equation number 2. And this is the one that's going to describe the rotational motion. Now look, there's 3 forces in my sketch. So in general, there could be 3 distinct torques in my sketch, but actually there's only one that's non-zero. The other 2 are 0. Firstly, the weight. The weight creates no torque. The weight creates no torque because it acts at the center of mass, which is the axis of rotation. And if you remember, the formula relates forces to torques, or torques to forces, that an important quantity in the torque is the distance you are, the forces acting from the axis of rotation. Here that distance is 0, absolutely 0. And so the weight creates no torque. Also, the normal force creates no torque for a different reason, though. It's acting at a distance from the axis of rotation, but it's acting in the direction towards the axis of rotation. So if you were to calculate the torque for the normal force, you'd be in the same situation as a potter's wheel. the force, normal force, and the vector from the axis of rotation to where that force is exerted at 180 degrees, opposite directions. And so sine of 180 is 0. So that normal force also creates no torque. And that's what I've denoted here. The only force creating a torque is the friction force. And the torque that it creates is the force times the distance from the axis of rotation, that's the radius of the blueberry or the cookie or the donut, times the sine of the angle between the vector to where the force acts and the force vector itself. That's 90 degrees. So this piece is just 1. And replace it with 1. And that torque determines the angular acceleration here, just like these forces determine the linear acceleration upstairs here. And so that's took me a while to describe that slide, but it's a really important slide. It's really important because it's distilling. I mean, this is one of the great slides in my lecture class. It's distilling a depth of understanding of Newton's law of rotation and Newton's law of translation, our understanding of the dynamics of rotation and translation into these two little equations that are describing the rolling sphere, cylinder, or ring. Now, if you look at those equations, it's interesting just to stand back from them, kind of admire the view and say, you know, what's in there that I know and what don't I know? There's a bunch of things you do know. You might know the mass of the blueberry and the radius of the blueberry. You might know the incline, the angle of the incline. We know how to calculate the moment of inertia of the blueberry. Things we don't know, for example, are, and things that we want to solve, are like the accelerations, the angular acceleration and the linear acceleration, the A and the alpha. And so that's our goal, right? If I want to know who wins this race, blueberry, gone, cookie or donut, I'm going to have to figure out the accelerations of the blueberry, cookie, and donut. And so somehow I've got to take this stuff, understanding, and find out A. Use it to figure out A, the linear acceleration. So let's see if we can do that. And I think that's the next couple of slides doing that. Okay, so this slide, really, I just took those two equations that I've already introduced based on, based on understanding translational motion and understanding rotational motion. And I've modified one of them. This one stayed the same. The translational motion dynamics stayed the same. The rotational motion dynamics, I've modified it a little bit. And specifically, what did I do? I put in two things, and I just listed them upstairs here. One of them, I put in this condition that the objects are rolling down the incline. And that condition, if you remember, relates linear and angular accelerations, linear and angular velocities, linear and angular displacements. And so one thing I'm going to plug in is this equation, A equals alpha R. So that's going to allow me to take the alpha and turn it into an A. And then the second thing I plugged in was from that table I showed you earlier. I looked up what the cylinder's moment of inertia is in terms of its mass and its radius. It's half mr squared. We even discussed that case. And so I plugged that in too. I replace I with half mr squared. Now, when you do that, you actually find an interesting thing. The R's, the radius of the blueberry or the cookie or the donut, feel like I'm on some neurological exam where I've got to remember these 3 words for the entire lecture, and I'm struggling. When you plug in the moment of inertia and you plug in that angular acceleration, you discover that the r's actually cancel out. And you end up with this really simple formula here that relates the frictional force and the acceleration. And at this point, let's look again. Let's stand back from these equations again, these 2 equations, and look at them again from the perspective of, you know, what we know and what we want. They contain A, we want that. They contain, you know, the mass of the rolling object, the angle of the incline, we might know that. And then they contain the frictional force. We don't really know that. But there are 2 equations now with 2 unknowns. The 2 unknowns are the A and the frictional force. And so now I've turned this problem into a math problem, right? I don't know what math class you would do this in, but Math 109, or whatever it is. This is 2 equations, 2 unknowns. This is why you do 2 equations, 2 unknowns in Math 109. And so we can solve this for, we could solve this pair of equations for the acceleration, we could solve it for the frictional force. I'm just going to solve it for the acceleration. And that's the next slide. And that's what I'm doing here. So I've reproduced on this slide equation number 1. I just wrote it down again. Reproduced the second equation, wrote it down again. And I want to combine these to solve for the acceleration. And actually, you might see a simple way you can do that. Just add the 2 equations together, which means adding the left-hand sides together, adding the right-hand sides together. You can do that here because in the first equation, we got negative frictional force. In the second equation, we got just the frictional force. If you add those 2 equations together, you're going to cancel out this friction. And you end up with this equation here. And this equation here is, if you rearrange it, your solution for the acceleration of the cylinder down the incline. You just need to divide through by the mass. The mass cancels out on the left and right hand side, and you get this result here. And it's very interesting to compare that result with what you would get if an object slid down an incline. If an object slides down the incline, you might remember this from all our work on Galileo's falling bodies. You get an acceleration that's g sine theta. It's a diluted version of the acceleration of gravity that depends on the angle of the incline. So you get this g sine theta. We've got that g sine theta again, because again, we're going down the incline, but we got additional factor, a new bit. And this new bit is always less than 1, and it's due to the rolling. It's a consequence of the rolling rather than just the sliding. And actually, the exact number, we got 2/3 here. The exact number depends on whether you were considering a cylinder or a sphere or a ring. We considered the cylinder. It depends on the exact equation for the moment of inertia. It depends on this piece, this number in that equation. And so it's a very interesting problem, this rolling of objects down inclines, where you've got this rotational and translational motion, where you can write down the description of the rotational and translational motion, and you can solve for the acceleration. So, next slide. Next slide was, so my solution, I've done with the solution now. I solved the case of the cylinder. You could do exactly the same thing. There's no point in us doing it for the sphere and the ring. And because the sphere and the ring and the cylinder have, I'm seeing lots of interesting comments about donuts now. I'm getting very hungry. Because the sphere and the cylinder and the ring have different moments of inertia, the sphere, the cylinder, and the ring have different accelerations. So that's really interesting. And I did this calculation earlier, so I wanted to summarize the results. Here in the middle is the cylinder. That's the one that we actually computed ourselves, where we used this moment of inertia, 1/2 mr squared. If you did the sphere, you get this equation here, and you'd be using this. Sorry, if you did the ring, sorry, this top one's the ring. If you did the ring, you get this equation here, and you'd be using this moment of inertia. And if you did the sphere, then you'd be using this other moment of inertia, and you get this equation here. You notice that, remember, the sphere has the smallest factor, 2/5. The ring has the largest one. There's really like a 1 here, and the cylinder's in between. Well, that maps into the accelerations. The sphere has the largest acceleration, the cylinder intermediate acceleration, and the ring the smallest acceleration. And so that's the solution to this problem. So I got a quiz here. So here we are in the large lecture room. I got the blueberry. It's a nice solid sphere. I got the cookie. That's a nice solid cylinder. And I got the donut, nice donut with a hole in the middle. I actually picked these 3 objects because these particular blueberries, donuts, and cookies all had the same mass and the same radius. So there's no question about one having a bigger or smaller mass, bigger or smaller radius. And then I raced them. And let me show you that again in slow motion. I'm going to slow it down. But I hope you can see that as we watch it in slow motion, the sphere is the winner. The cylinder came in second, and the ring is third. The winner is the sphere with the smallest moment of inertia. It had the largest acceleration. The loser was the ring that had the largest moment of inertia and had the smallest acceleration. And so sphere wins the race.